Hey everyone, welcome. I'm absolutely thrilled you're here for this explainer. Think of me as your personal networking trainer today, because we're going to completely demystify how the internet actually works. You know that exact millisecond you hit enter on your keyboard? It feels instant, right? Well, your data is actually kicking off this epic, highly orchestrated journey behind the scenes. So let's just dive right in and uncover the hidden architecture of the web.
All right, Phase 1. Setup, your device identity. Before we go anywhere, how does a brand new device even get recognized on a network in the first place?
Well, it happens through a process called DHCP. You can kind of think of DHCP as the welcome desk of your local network. When you first connect, your device literally shouts out with a discover message. The network hears it and responds with an offer. Then your device sends back a request to say, yeah, I'll take that. And finally, the network locks it in with an ACK or an acknowledgement. Through this really quick four-step sequence, DHCP hands your device its temporary ID badge. And just like a real visitor badge, this lease eventually expires and has to be renewed.
So that ID badge it just got? That's your IP address. It's basically a unique software location given to every single device sitting on a subnet, like in our example here, 192.168.1.4. This setup means every device gets its own address, letting unique hosts sit together on the same local subnet. It's exactly how the data knows, which specific laptop in your house asked for a web page instead of, say, your smart TV.
But here's the thing, your device actually has a second identity. While the IP address is temporary, it changes depending on what coffee shop or house you're at, your MAC address is permanent. This is your network interface card's actual hardware identity, and it's literally burned in at the factory. It looks like a string of letters and numbers, something like 3C:22:FB:9A:41D7. The absolutely crucial takeaway here is that while your IP address helps navigate the wider world, your MAC address is your physical hardware identity, and it never, ever leaves your local network.
Which brings us perfectly to Phase 2, escaping the local network. Our data is all packed up, but how does it actually prepare to leave the house? First off, it needs to understand the boundaries of its own neighborhood. That's exactly where subnetting and CIDR come into play. Basically, this is just a process of splitting massive networks into smaller, manageable subnets. You might see a notation like a /16. That mask literally draws a line right down the middle, separating what part of the address represents the whole network and what part represents your individual host device. It's exactly like distinguishing between your street name and your specific house number.
Okay, so as our data tries to leave, it's going to encounter some traffic directors. Let's compare the two big ones, a switch versus a router. A switch is strictly a local worker. It only connects traffic within one single network, and it does that using those factory-burned MAC addresses we just talked about. But a router? Well, the router is your gateway to the rest of the world. It connects traffic across totally different networks by looking at IP addresses.
But right before your router sends your data out the front door, it pulls off this brilliant trick called NAT, or Network Address Translation. See, you probably have a whole bunch of devices at home with private IP addresses, like 10.0.0.12. The problem is, the internet can't route data back to a private internal address. So NAT steps in as a translator. It rewrites your private inside IP into one shared public outside IP, like 203.0.113.5. So you have all these many private IPs, all presenting just one single public face to the outside world. Pretty clever, right?
All right, our data hero has successfully escaped the local network. We are now officially entering Phase 3, traveling the open internet. This is where things get seriously fast.
Let's say you typed a name into your browser, like algoinsight.io. Here's a fun little secret. That name means absolutely nothing to a router. Routers only speak math. They only understand IP addresses. So enter DNS. You can think of DNS as the ultimate internet phone book. It takes that human-readable name and resolves it into a machine-readable IP address, like 216.150.1.193. And the best part? It does this lookup once and then caches the result to speed the whole thing up for the next time you visit.
Now, let's zoom out a second and see how all this builds into the grand architecture of the internet, the OSI model. Data passes through 7 distinct layers. Starting way out the bottom with the physical cable on layer 1, it moves up through the MAC address, the IP, TCP, and TLS security, all the way up to layer 7, which is the actual application you're looking at on your screen. It's essentially the master blueprint of all internet communication.
But you have to remember, your data doesn't travel across those OSI layers as one giant clunky block. If it did, it would totally clog up the system. Instead, a single file gets split into thousands of tiny little chunks called packets. This is what allows the data to travel so incredibly efficiently across the network. Each packet weaves through whatever path happens to be the fastest at that exact millisecond. Then, once all those tiny packets arrive at their destination, they're perfectly reassembled in exact order.
But how do they know how to behave on that journey? Well, that depends on the transport rules. TCP versus UDP. They might travel on the exact same wire, but they offer two totally different promises. TCP is your reliable stream. It guarantees that every packet is ordered and formally acknowledged. If a packet gets lost, TCP says, hold on, resend that. UDP, on the other hand, is built entirely for speed. It's a fast datagram using a fire and forget policy. It literally doesn't care if a packet drops, it just keeps pushing data forward. That makes it absolutely perfect for live video streams or gaming, where sheer speed is way more important than absolute perfection.
We've crossed the wild internet, and we are finally at our last stage, Phase 4, reaching the servers safely. Because let's face it, arriving is really only half the battle. We have to make sure our data arrives securely. Let's look at the difference between HTTP and HTTPS. They might target the exact same website, but they are two completely different bets. Standard HTTP is basically the web without a lock. If you send a password, say Hunter2, over HTTP, literally anyone listening on the network can read it in plain text. Not great. But HTTPS, that S stands for secure. It slaps a digital lock on there, encrypting your data so that only the actual destination server can understand it.
So how does that lock actually get created? It happens through the TLS handshake. Before any sensitive data even thinks about moving, the client and the server have a little introductory meeting. They exchange a hello, they pass a digital certificate to prove their identity, and they swap an encryption key. Actually, only after this handshake is totally complete does the real data transfer begin. It's a non-negotiable step that ensures everything that follows is fully encrypted and safe from prying eyes.
As our data is practically touching the server, it has to clear a few final security checkpoints. First up, ports. A server only has one IP address, but it has many doors. The port number picks the exact service you want, like port 80 for normal HTTP web traffic or port 22 for secure SSH access. Next is the firewall. Think of this as the bouncer. It evaluates security rules in order. The gold standard here is default deny, meaning it just blocks everything by default and only explicitly allows the good traffic through. And finally, if you're using a VPN, you've essentially wrapped your entire journey in a private encrypted tunnel. The exit node knows what's going on, but your local internet service provider, they just see one giant, indistinguishable blob of encrypted traffic.
And just like that, boom, our data has arrived. Now, I want to leave you with this final kind of mind-bending thought. Considering the sheer complexity of these 15 steps we just walked through, from DHCP leases and NAT translations all the way to DNS lookups and TLS handshakes, how many thousands of times do you think this exact journey happens every single second you're online? The speed and scale of the internet is truly just a modern marvel. Thank you so much for joining me on this explainer. I hope you're walking away with a much clearer picture of how it all connects. Keep learning, and I'll catch you next time.